A synchronous counter is a digital circuit that counts in binary or any other radix where all flip-flops receive the clock pulse at the same time, unlike an asynchronous ripple counter, where the clock ripples from one stage to the next. Think of it as a team of workers flip-flops who all start a step together when a whistle clock blows. The operation principle is that the next state of each flip-flop is a deterministic function of the present state of the whole register. Because the clock is common, the transition happens in one clock cycle, giving predictable timing. The characteristic or excitation table for a single D-type flip-flop is simple: Q plus equals D. For JK and T flip-flops, the table shows required JK or T inputs to move from current state Q to next state Q plus. By stacking these tables for each bit, we obtain the characteristic table of the whole counter, which lists present state to next state for every binary combination. For an n-bit synchronous up counter, the table is just a binary count: 0, 0, 0 to 0, 0, 1 to 0, 1, 0 to 0, 1, 1 to 1, 1, 1 to 0, 0, 0. For a down counter, it runs in reverse. The table is the blueprint for designing the required combinational logic that drives the flip-flops. JK flip-flops are versatile because they can hold, toggle, set, or reset based on J and K inputs. The excitation table for a JK flip-flop is Q present Q plus next JK. 0 to 0 gives J0 don't care, 0 to 1 gives J1 don't care, 1 to 0 gives don't care K1, 1 to 1 gives don't care K0. X means don't care. From the global characteristic table of the counter, we write, for each bit I, the required J sub I and K sub I as Boolean functions of the present state bits Q0 through Qn-1. Excitation equations example for a 3-bit up counter. J0 equals 1, LSB always toggles. K0 equals 1, so J0 and K0 equals 1 toggle. J1 equals Q0, toggle when Q0 equals 1, i.e. when the LSB rolls over. K1 equals Q0, same as J1. J2 equals Q0 and Q1, toggle when the lower two bits are 1, 1. K2 equals Q0 and Q1. These equations are derived by comparing the present state and next state columns. Once the Boolean expressions are ready, we draw the combinational block and/or NOT gates that generates J and K for each stage, then connect them to the JK flip-flops. The clock line is shared among all flip-flops, giving a fully synchronous design. Circuit synthesis involves 1. Write excitation equations. 2. Simplify them using K-map Quine-McCluskey. 3. Implement using the smallest number of gates. 4. Verify that the resulting circuit produces the desired state transitions. A T-toggle flip-flop changes its output on every clock edge when T equals 1. If T equals 0, it holds its current value. Q0 Q plus 0 T0, Q0 Q plus 1 T1, Q1 Q plus 0 T1, Q1 Q plus 1 T0. Thus, the required T input for a transition is simply T equals Q exclusive or Q plus, XOR of present and next state. For a synchronous up counter, each bit toggles when all lower order bits are 1, that is when they overflow. Hence the excitation T functions become T sub 0 equals 1, LSB always toggles. T sub 1 equals Q sub 0. T sub 2 equals Q sub 0 and Q sub 1. T sub 3 equals Q sub 0 and Q sub 1 and Q sub 2. These are derived directly from the rule. Bit I toggles when bits 0 through I-1 are all high. Circuit synthesis with T flip-flops is even simpler than with JK flip-flops because each stage needs only a single input. After writing the toggle equations, we minimize them using Carnot maps. For example, T sub 2 equals Q sub 0 and Q sub 1 may already be minimal. The final hardware consists of a cascade of AND gates feeding the T inputs, plus the shared clock line. If a down counter is required, the toggle condition becomes the complement of the lower bits. For example, T sub 1 equals not Q sub 0, T sub 2 equals not Q sub 0 and not Q sub 1, etc. The procedure remains the same. Derive T equals Q exclusive or Q plus, simplify, and wire the gates. A mod N counter counts from 0 to N-1 and then resets to 0. The state table lists N rows, each row showing the present binary state and the next state. usually the binary representation of present plus 1 mod n for n not equal to a power of 2, some binary codes are unused and must be detected to force a reset. Choose the smallest n such that 2 to the n is greater than or equal to n. Example: mod 10 needs n equals 4, 2 to the 4 equals 16. Create the state table for the 2 to the n possible codes, marking the first n codes as valid counting states and the remaining 2 to the n minus n codes as illegal. Derive next state equations for each flip-flop using the excitation method. JK or T for valid states, the next state is present plus 1 mod n. For illegal states, the next state is forced to all zeros. Modulus selection logic detects the illegal codes. For example, for mod 10, the codes 1010 through 1111. A combinational decoder generates a reset pulse, often called mod reset or load. This pulse forces all flip-flops to 0 on the next clock, completing the modulus. Mathematically, let m equal 2 to the n minus n be the number of illegal states. Define a detection function r equals sigma of illegal code sub I, which is the OR of all minterms representing illegal codes. When r equals 1, a synchronous reset line, often connected to the clear input of the flip-flops, is asserted for 1 clock cycle. The final circuit therefore consists of the regular synchronous counter core plus the modulus selection block that monitors the state and injects a synchronous clear when the count reaches n. For example, for mod 10, illegal codes are 101010, 101111, 110012, 110113, 111014, 111115. The detection function can be simplified to r equals q3 and open parenthesis q1 plus q2 close parenthesis, which is used to drive the clear input of the flip-flops. Explanation: up/down synchronous counter architecture and control signal generation. An up/down counter can count upward or downward based on a control input u/d. 1 equals up, 0 equals down. The architecture typically uses the same flip-flop array as a normal counter, but the combinational logic that generates the excitation signals is made conditional on u/d. For a T flip-flop implementation, the toggle equations become: T sub 0 equals 1, always toggles regardless of direction. T sub 1 equals open parenthesis u/d close parenthesis, dot q sub 0 plus u/d bar dot q sub 0 bar. T sub 2 equals open parenthesis u/d close parenthesis, dot q sub 0 dot q sub 1 plus u/d bar dot q sub 0 bar dot q sub 1 bar. And so on. Explanation: when counting up, a bit toggles only when all lower bits are 1. When counting down, a bit toggles when all lower bits are 0. The term u/d selects between the two conditions. For a JK flip-flop design, the excitation equations are similar but include both J and K signals. Often designers use a mux 2-to-1 multiplexer for each excitation input. One input of the mux is the up condition expression, the other is the down condition. The select line is u/d. Control signal generation. Direction pin u/d drives the multiplexers. An optional load input can preset the counter to a specific value, useful for start at n. A carry out or borrow out can be produced by detecting the terminal count, for example all ones for up, all zeros for down, and an or ing with u/d. The resulting block diagram shows clock arrow flip-flops arrow excitation logic arrow u/d. All flip-flops share the same clock, ensuring synchronous operation. Real-world analogy: think of a digital elevator panel that can move up or down floors. The floor number is stored in a register. Pressing up or down changes the direction signal, which decides whether the register increments or decrements on each tick of the floor sensor clock. Karnaugh map minimization of excitation functions for minimal gate implementation. K-maps are a visual method to simplify Boolean expressions. For each flip-flop's excitation J, K, or T, we plot a K-map with the present state variables q sub 0 through q sub n-1 as inputs. The cells where the excitation must be 1 are marked 1. Don't care states, illegal codes in mod n counters are marked X and can be used to enlarge groups. A procedure. Step 1. Write the excitation truth table for the target flip-flop. Step 2. Transfer the 1s and X's onto a 2 to the n cell K map, where n equals the number of present state variables. Step 3. Form the largest possible groups of 1, 2, 4, 8, and so on cells including X's when beneficial. Step 4. Derive the simplified product term for each group. The sum of these terms gives the minimized sum of products expression. Example, for a 4-bit mod 10 counter, the T sub 2 excitation toggle of Q sub 2 is 1 for states where Q sub 1 dot Q sub 0 equals 1, binary 11, and the count is less than or equal to 1001. The K map yields the minimal expression T sub 2 equals Q sub 1 dot Q sub 0 dot not Q sub 3. The extra not Q sub 3 eliminates illegal states 1010 through 1111. This is smaller than the raw product Q sub 1 dot Q sub 0. The benefit of minimization: fewer logic gates leads to lower propagation delay, reduced power, and smaller silicon area. In exam problems, a well-drawn K map often earns full credit even if the final expression is not the absolute minimum. Tip: always include the illegal states as don't care states. They are the key to shrinking the logic for mod n counters. Timing tells us how fast the counter can run without errors. Propagation delay, T sub PD, of a combinational gate is the time from a change on its input to the resulting change on its output. In a cascade of gates, for example the AND/OR network that creates J/K/T, the total delay is the sum of the individual gate delays along the longest path, the critical path. Clock-to-output delay, T sub CQ, of a flip-flop is the time from the rising or falling clock edge to the moment the Q output reflects the new state. It is usually specified in the datasheet, for example 8 nanoseconds for a typical JK flip-flop. Maximum operating frequency, Fmax, is limited by the worst-case time a state needs to settle before the next clock edge. TCLK min equals T sub CQ plus T sub PD plus T sub setup. Fmax equals 1 divided by TCLK min, where T sub setup is the required setup time of the flip-flop. Time the excitation input must be stable before the clock edge. For a synchronous counter, all flip-flops share the same clock, so the critical path typically goes through the combinational logic that generates the excitation for the most significant flip-flop, the T sub CQ of that flip-flop. Example, assume each 2-input AND gate has T sub PD equals 2 nanoseconds. The excitation for Q3 uses 3 AND gates in series, total 6 nanoseconds. The JK flip-flop has T sub CQ equals 8 nanoseconds, and T sub setup equals 1 nanosecond. TCLK min equals 8 nanoseconds T sub CQ plus 6 nanoseconds logic plus 1 nanosecond setup equals 15 nanoseconds. Fmax approximately 66 MHz. If the clock period is set to 20 nanoseconds, 50 MHz, the counter will work reliably. Timing analysis is essential when the counter is part of a high-speed system, such as a digital video processor. Practical tip: always add a safety margin 10 to 20% to Fmax to tolerate temperature and voltage variations. Important numerical problem: design of a 4-bit decade mod 10 synchronous counter. Goal: build a synchronous counter that counts 0 to 9 and then returns to 0 using JK flip-flops. A step-by-step solution: choose hardware: 4 JK flip-flops Q3, Q2, Q1, Q0. Clock is common. State table present to next for count 0 to 9, binary 0000 to binary 10001. After 10001, the next state must be 0000. Excitation table for each flip-flop present Q next Q plus gives required JK. For Q0 least significant bit, toggles every step so J0 equals K0 equals 1. For Q1 toggles when Q0 equals 1 on a carry from least significant bit, therefore J1 equals K1 equals Q0. For Q2 toggles when Q1 and Q0 are both 1 and the count is less than or equal to 1001. Raw expression is Q1 and Q0, but we must suppress toggling for illegal states 10 to 15. Adding a don't care term gives J2 equals K2 equals Q1 and Q0 and not Q3. For Q3, most significant bit toggles when Q2 and Q1 and Q0 are all 1, and the count is less than or equal to 1001. This only occurs for the transition 0111 to 1000. Hence J3 equals K3 equals Q2 and Q1 and Q0, and not Q3. Simplify with K-maps as shown in the previous topic. The minimal expressions are J0 equals K0 equals 1, J1 equals K1 equals Q0, J2 equals K2 equals Q1 and Q0 and not Q3, J3 equals K3 equals Q2 and Q1 and Q0 and not Q3. Mod 10 detection logic illegal states are 101010 to 111115. A simple detection function is R equals Q3 and open parenthesis Q1 or Q2 close parenthesis. Connect R to the clear or preset input of all 4 JK flip-flops so that on the next clock edge all QS becomes 0. Gate implementation. And gate for Q1 and Q0 and not Q3 3 input and with an inverter on Q3. 4 input and for Q2 and Q1 and Q0 and not Q3. Or gate for Q1 or Q2 feeding the detection and with Q3. Timing check using typical gate delays of 2 nanoseconds flip-flop TCQ 8 nanoseconds T, setup 1 nanosecond. Critical path through J3 K3 logic 2 nanoseconds, inverter plus 2 nanoseconds times 3 for the N equals 8 nanoseconds. Minimum clock period equals 8 nanoseconds TCQ plus 8 nanoseconds logic plus 1 nanosecond setup equals 17 nanoseconds, giving maximum frequency approximately 58 MHz. The resulting circuit is a compact, fully synchronous decade counter, suitable for applications such as digital clocks or frequency dividers. Key takeaways: use the JK excitation table, treat illegal codes as don't cares, and add a synchronous reset that forces the count back to 0. Explanation: typical exam type questions and concise solution strategies for synchronous counter design. Question 1: design a 3-bit synchronous up counter using T flip-flops, provide the excitation equations, and draw the minimal gate diagram. Write the binary count sequence 000 to 001 to 010 to 0, 11 to 1 00 to 1 01 to 1 10 to 1 11 to 000. Derive toggle condition: T0 equals 1, T1 equals Q0, T2 equals Q0.Q1. Simplify parenthesis, already minimal parenthesis. Draw one inverter for Q0 if needed. 1 2 input and for T2 and connect T inputs to the T flip-flops, show common clock. Question 2: given a mod 6 counter implemented with JK flip-flops, list the J and K expressions for each flip-flop. 3-bit register since 2 to the 3rd equals 8 greater than or equal to 6, write state table for 000 to 101. Then force 110/111 to 000. Use JK excitation table to get J/K for each transition. Treat 110/111 as don't care, simplify with K maps. Typical result: J0 equals K0 equals 1, J1 equals K1 equals Q0, J2 equals K2 equals Q0.Q1. not Q2 or similar. Question 3: explain how to convert an asynchronous ripple counter into a synchronous one, and discuss the timing advantage. Identify that ripple counter's clock to each stage is the Q output of the previous stage, causing cumulative propagation delay. Replace the cascading clocks with a single common clock. Add combinational logic that generates the proper J/K/T inputs based on the whole present state. Emphasize that maximum delay becomes 1 flip-flop T sub CQ plus 1 combinational path independent of the number of bits, allowing much higher Fmax. Question 4: design an up-down 4-bit counter using JK flip-flops with a direction control input D. Provide the equations for J3 and K3. Write up condition: J3 up equals K3 up equals Q2.Q1.Q0. Down condition: borrow J3 down equals K3 down equals not Q2. not Q1. not Q0. Use a 2-to-1 multiplexer controlled by DJ3 equals D.J3 up plus not D.J3 down, same for K3. Show the multiplexer schematic. Question 5: calculate the maximum clock frequency for a 5-bit synchronous counter whose combinational logic delay is 12 nanoseconds, flip-flop T sub CQ equals 7 nanoseconds, and setup time equals 1 nanosecond. T clock min equals T sub CQ plus logic delay plus T setup equals 7 plus 12 plus 1 equals 20 nanoseconds. Fmax equals 1 divided by 20 nanoseconds equals 50 MHz. General exam tips. Always start with the state characteristic table, it anchors the whole design. Use don't care states for mod n counters, they simplify logic drastically. When asked for gate count, draw k maps and count the prime implicants. Remember to mention the synchronous clear reset for modulus selection. Include timing formulae t clock min to prove the counter meets the required speed. Keep the answer organized I state table Roman 2, excitation equations Roman 3 minimization, Roman 4 circuit diagram sketch V timing check. General exam tips. Always start with the state characteristic table, it anchors the whole design. Use don't care states for mod n counters, they simplify logic drastically. When asked for gate count, draw k maps and count the prime implicants. Remember to mention the synchronous clear reset for modulus selection. Include timing formulae t clock min to prove the counter meets the required speed. Keep the answer organized I state table Roman 2, excitation equations Roman 3 minimization, Roman 4 circuit diagram sketch V timing check.